Hello, Grade 6. Today we get an extra special edition, a bonus edition of Grade 6 Nelson Math Textbook, Section 13 or Chapter 13, Section 5, Number 5. Let's read it together. Randomly choose two different vertices of the hexagon. A. Determine the theoretical probability that a line segment joining them is longer than the side length of the hexagon. Use a tree diagram. B. Determine the theoretical probability that the letters of both vertices come before E in the alphabet. Let's do some defining of terms first. So, where two lines meet, at this point, that's called one vertex. Where we have more than one, or plural, they're called vertices. So A is a vertex where these two lines meet, but A and B are two vertices. A and C and D are three vertices. So just so we get some of that terminology out of the way. So for this question, we have to choose two different vertices, but we're supposed to choose them randomly. We don't know which ones they're going to be. So we have to somehow organize ourselves, and we've been told to use a tree diagram, which I've done down here. So we are going to A, determine the theoretical probability that a line segment joining them is longer than the side. So let's go through these terms. Theoretical probability, we must organize ourselves, and we're not going to be doing the actual experiment. For example, we're not going to be writing down A, B, C, D, E, and F on pieces of paper and picking them out one at a time. That would be experimental probability, but we're not. We're going to use a tree diagram to figure out its theoretical probability. A line segment would be this line right here. That is one line segment. The distance from A to B. That's a line segment. Another line segment is the distance from B to C. Another line segment, if we drew it, would be the line segment from A to C. Now, we didn't draw that, but if we drew it, it would be a line segment. The length of one side of the hexagon would be A to B, which is equivalent or the same length as A to F, or F to E, or E to D. To further define this, A to B is not as long, or it's shorter than, the distance from A to C. D to A is different and is longer than the line segment A to B. So it's bigger than the length of one side. Now that we have all the terms figured out, let's see if we can come up with a tree diagram that makes sense. So if we look here, let's make an organized tree diagram. And I'm going to start off with saying, let's find all the different outcomes where I choose A. If I choose A, I have the following outcomes. I have A, which can meet B, and we'll call that AB. I have A, which can meet C, and I'll call that AC. I have A, which can meet D, and I'll call that AD. A meets E, AE. A meets F, AF. Now let's look for these line segments on the hexagon here. This is AB, this line segment right here. That's AB. AC is a line segment that would go from this point to this point. AD is a line segment that would go from this point to this point. AE is a line segment that goes from this vertex to this vertex. AF is a line segment that goes from this vertex to this vertex. So those are all the line segments that we made with this right here. Now it's asking which of these, AB, AC, AD, AE, and AF, would be longer than one side length. We have only one side length here, but it's repeated 6 times. Side length, side length, side length, side length, side length, side length. Those are all the side lengths. So which ones of these 5 are longer than these side lengths? Here to here, for example. AC is longer than the side length. AD is longer than the side length. AE is longer than the side length, and I've labeled them right here. AC, AD, and AE are longer than the side length. AB is a side length, which means necessarily it is the same length as the side length. And AF is also the same length as the side length. We would have to repeat this 5 more times. So we would do here B, which could be approached to A, C, D, E, and F. And then C can be approached to A, B, D, E, and F. And then D can be, after all of that, after we do all of those, we would see that 18 of the 30 different outcomes, which we would all label, 18 of the 30 would be longer than the side length. So I've made it to 3 over 5. 18 over 30 is equivalent to 3 over 5. So it's 60% or 0.6 in decimal form. Now let's read B. Determine the theoretical probability that the letters of both vertices come before E in the alphabet. E is not before E, so it would only be for the ones that are A, B, C, and D for both vertices. Both vertices must be A, B, C, and D. So if we were looking for a pair that met this criteria, A and B, vertex A, vertex B, would be both before the E in the alphabet. But A, F would not meet that criteria because F comes after E. So let's count them. Here's the tree diagram that has all the outcomes that begin with A. Here we have the tree diagram where all outcomes begin with B. Here we have all the tree diagrams where outcomes begin with C. Outcomes begin with D. Outcomes begin with vertex E. And outcomes begin with vertex A. Let's count them now. So remember, both letters must be before E in the alphabet. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. None of them here will meet that criteria because they all have an E. None of them here will meet that criteria because they all have an F. So for this one, we would have 12 outcomes meeting that criteria that both vertices have letters that come before E in the alphabet. And I've labeled that right here. 12 outcomes out of a total of 30 outcomes, and they're all listed in all of these pages here. If I counted all of these boxes, there would be 30 outcomes, and that makes sense because I have 6 tree diagrams, and every tree diagram has 5 branches. So 12 out of the 30 have both vertices A, B, C, or D. So I've written an equivalent fraction, 12 over 30. I can rewrite the 12 over 30 in an equivalent fraction as 2 over 5 in lowest terms. And that's how we complete this question. Thanks, everyone. Have a good day.